In this video, we're giving the text needed to explain the law of or Lenz's law with the help of conservation of energy. So in the last video, I did explain it, but let's look at it again. So we have understood that a changing magnetic field will induce EMF and current. Then we got to see the law related to this, telling that if you change it faster, the induction is more. And whatever time you change it, during that time, we see the induction, not anywhere else. And the third thing that we got to understand is the directional aspect. So, directional aspect again was to do with or is to do with energy conservation. So, we can't just generate energy somewhere. Current is nothing but we're pushing and pulling electrons at the simplest manner. We can't push and pull something without spending energy. Makes sense, right? Now, how is that spending energy happens over here? Well, that's what the law talks about. When a magnetic field changes, it induces a current in a nearby conductor. That we know. Right? This is a fact. So according to the Lenz's law, the induced current generates its own magnetic field that opposes the change in the original magnetic field. So it opposes the change. This opposition requires work to be done against the induced magnetic field to maintain the motion, causing the change in the magnetic field. Make sense? Now, example. So when we push a north pole of magnet towards the coil, the induced current in the coil creates a magnetic field with its own north pole. North pole going towards creates a north pole. This opposes the north pole, resists the motion of the magnet, required you to exert force to continue pushing. So we are doing something, right? If this was not there, if I push a little, if this turns out to be south, the south will pull the north, and with a small push, you have an infinite energy. How is that possible? It's not possible. You have to do work to push the magnet against the opposing force. This mechanical energy you exert in pushing the magnet is converted to electrical energy. So energy can be transferred from one form to another form. That's what it's coming to. If I do the opposite, right? This is me pushing it, so this will become north. So this will oppose, right? This will oppose. Every time it's opposing basically. In what form of opposition, that depends. Conversely, if you push the magnet away from the coil, or pull the magnet, sorry, not push, pull the magnet away from the coil, the current will reverse the direction. This time the coil generates a magnetic field with its south facing the retrieving coil against opposing motion. The mechanical energy you use to push and pull the magnet is converted to electrical energy in the form of a induced current in the coil. As simple as that. So finally, we'll end such a question. If they ask you to verify or explain with the help of conservation of energy, the Lenz's law, you have to end it with this. What is this? This could have been done better. So what we are looking at here is, say we have a magnet and say this is north and this is south, and we are pushing it, right? And as per our right hand rule, so this has to be south. Again, this is not a right scenario, but we're just showing what happens. If Lenz's law did not hold, the induced current would enhance the change in magnetic field, leading to, this is never ending, right? Perpetual increase in energy without an external work. This would violate the law of conservation of energy. This is important when you're writing this explanation with the law of conservation of energy. This paragraph is important. Everything else is example and all of that. So finally, to conclude, Lenz's law is a consequence of law of conservation of energy. Okay, guys. Again, it's the same funda. We have to do work to transfer work. it's based on that fact.